Imagine a force so powerful it can twist the fabric of space itself, bending stars into oblivion and shaping the destiny of entire galaxies. These are the invisible hands of extreme magnetic fields, cosmic titans, lurking in the darkness, orchestrating some of the most violent and breathtaking phenomena in the universe. We're talking about fields so intense they could rip atoms apart, warp time, and even resurrect dead stars from their ashes. And yet, despite their terrifying power, they remain one of the universe's best-kept secrets, hidden in plain sight. Magnetic fields are everywhere, woven into the fabric of space, guiding the birth of stars, the death of black holes, and the dance of planets. But when these fields reach their most extreme, they become something else entirely. Picture a neutron star, its surface so magnetized that a single teaspoon of its material would weigh billions of tons on Earth, crushed by the sheer force of its own magnetism. Or consider the monstrous fields near supermassive black holes, where magnetic storms rage with enough energy to light up entire galaxies for centuries. These aren't just scientific curiosities, they're the engines behind the universe's most dazzling light shows and its most destructive catastrophes. Today, we're diving deep into the heart of these magnetic monsters, uncovering 30 astonishing facts that will redefine how you see the cosmos. From the bizarre physics of magnetars to the unexplained mysteries of intergalactic magnetic webs, each revelation will pull you deeper into the wonder and the terror of these unseen forces. By the time we're done, you'll never look at a simple refrigerator magnet the same way again. So buckle up. We're about to journey into the extremes where the laws of physics warp and the universe reveals its most magnetic secrets. If our sun's magnetic field is like a whisper, then a magnetar's is a deafening cosmic scream, one so powerful it defies comprehension. These neutron stars aren't just dense remnants of supernova. They're the universe's ultimate magnetic monsters, with fields reaching up to 10 quadrillion times stronger than Earth. To put that into perspective, a magnetar's pull could strip the information off a credit card from halfway to the moon or worse. Warp the very atoms in your body into thin, stretched-out needles. The birth of a magnetar is as violent as its existence. When a massive star collapses in a supernova, its core doesn't just settle into a quiet afterlife as a neutron star. Under the right conditions, like rapid rotation and turbulent, swirling plasma, it transforms into something far more extreme. The star's magnetic field, already intense, gets amplified to unimaginable levels as its matter crushes down into a city-sized sphere. The result, a magnetar, a celestial object so magnetized that its eruptions can shake the fabric of space-time itself. And those eruptions are no joke. Magnetars occasionally release starquakes, massive fractures in their rigid crusts that unleash bursts of gamma rays and X-rays. Some of these flares have been detected clear across the galaxy, packing more energy in a fraction of a second than our sun emits in thousands of years. But the real terror lies in their magnetic grip. If you ventured too close, the field would literally pull electrons from your atoms, reshaping matter at the most fundamental level. Even from light years away, their influence is undeniable. Magnetars have been caught slowing their own spins, their magnetic brakes working against the very laws of physics we thought we understood. What makes these objects even more fascinating is how rare they are. Of the billions of neutron stars in our galaxy, only a handful have been confirmed as magnetars. Yet their impact is anything but small. They challenge our understanding of matter, magnetism, and the limits of cosmic violence, proving that even in the vastness of space, some forces are too extreme to ignore. The magnetic fury of a magnetar doesn't just bend the rules of physics, it shreds them entirely. Picture an atom, the fundamental building block of everything you see around you. Normally, electrons orbit their nucleus in neat, stable shells held together by electromagnetic forces. but in the presence of a magnetar's field, those forces become irrelevant. The pull is so unimaginably strong that electrons get yanked straight out of their orbits, leaving behind naked atomic nuclei and a soup of dismembered particles. This isn't just distortion, it's annihilation, tearing matter apart at its most basic level. Scientists call this nightmarish state magnetic stripping, and it creates conditions so extreme they can't be replicated anywhere else in the universe, not even in the most advanced labs on Earth. Under ordinary circumstances, gravity or pressure might crush atoms, but a magnetar's magnetism overrides everything else. The field twists particles into elongated, needle-like shapes, aligning them like soldiers in formation to its whims. If you could survive long enough to observe it, the very structure of materials would become unrecognizable solid matter behaving like liquid, stretched and warped beyond imagination. Theoretical physics suggests there's an upper limit to how strong a magnetic field can get before it collapses under its own energy, a boundary known as the Schwinger limit. Magnetars don't just approach this limit, they laugh at it. Their fields are so intense they create quantum effects where empty space itself starts to crackle with particle-antiparticle pairs, a phenomenon normally only seen in particle colliders or the earliest moments of the Big Bang. It's as if the magnetar is tapping into the universe's raw code, rewriting the rules of matter in real time. And here's the terrifying part: we've only glimpsed the aftermath of this destruction. When magnetars flare, their magnetic quakes send shockwaves through space, detectable across millions of light years. In 2004, a single eruption from a magnetar 50,000 light-years away temporarily ionized Earth's upper atmosphere, disrupting radio communications and satellites. That's the equivalent of a cosmic burglar picking a planet's pocket from halfway across the galaxy. Yet for all their destructive power, magnetars are also cosmic crucibles, forcing scientists to rethink how matter behaves under conditions so extreme they border on mythology. Every flare, every twisted atom is a clue to understanding the universe's most brutal forces, and perhaps one day harnessing them. When a magnetar's crust cracks under magnetic pressure, the universe feels it. These aren't just tremors, they're cataclysmic starquakes, the most violent seismic events in the cosmos. Imagine a neutron star's surface, a lattice of atomic nuclei packed so tightly they form a crystalline crust harder than diamond. Now picture the unimaginable strain of magnetic fields billions of times stronger than Earth's, twisting and stretching that crust until snap. The star's rigid exterior fractures, releasing enough energy to light up the galaxy. The aftermath is spectacular. As the crust shifts, magnetic field lines snap and reconnect, triggering bursts of gamma rays so bright they temporarily outshine entire galaxies. In December 2004, Magnetar SGR 180620 demonstrated this with terrifying clarity. A starquake on its surface unleashed a gamma-ray flare in half a second that carried more energy than our Sun emits in 150,000 years. For a brief moment, that pinpoint of light outshone the full moon despite being 50,000 light-years away. Satellites designed to detect nuclear weapon tests actually thought Earth was under attack, triggering emergency protocols before astronomers identified the true culprit. But what makes these quakes possible? Unlike Earth, where tectonic plates slide, magnetar quakes are all about magnetism run wild. The star's interior is a superfluid soup of neutrons, while its crust remains locked in place by the titanic magnetic field. As that field evolves, twisting, kinking, and storing energy like a cosmic rubber band, it stresses the crust beyond endurance. When the tension finally breaks, the entire star rings like a bell, sending electromagnetic shockwaves rippling through space. Some starquakes even alter the star's rotation, like a skater suddenly tucking their arms in mid-spin. And the danger isn't just theoretical. In March 1979, astronomers detected a gamma-ray burst so intense it saturated every detector in Earth's orbit. Later traced to a magnetar in the Large Magellanic Cloud, This single event, lasting just 0.2 of a second, released more energy than our Sun will produce in its entire 10 billion-year lifetime. The wavefront of X-rays and gamma rays expanded outward at light speed, ionizing gas clouds across intergalactic space like a pebble dropped in a cosmic pond. These outbursts force us to rethink what solid even means in the universe. A magnetar's crust isn't just under pressure, it's a battleground where magnetism overpowers the very nuclear forces holding matter together. Every crack, every flare is a reminder that in the darkest corners of space, the laws of physics become suggestions. And as we detect more of these events, each one peels back another layer of mystery, showing us just how little we truly understand about the universe's most extreme magnetic prisons. Deep in the heart of our galaxy, hidden behind thick clouds of cosmic dust, lurks a magnetic behemoth, Sagittarius A, the supermassive black hole anchoring the Milky Way. While its gravitational pull is legendary, dragging stars into reckless orbits, its magnetic influence is just as staggering and far more mysterious. Recent observations reveal something unexpected. This black hole isn't just a vacuum cleaner for matter. It's a cosmic particle accelerator, armed with magnetic fields powerful enough to sling matter across space at nearly the speed of light. Picture the chaotic dance of gas and dust swirling toward the black hole's event horizon. Gravity pulls it inward, but magnetism flings it outward in colossal jet streams of high-energy particles stretching for thousands of light years. These jets aren't random. They're sculpted by magnetic fields so intense they act like invisible highways, guiding charged particles with pinpoint precision. Some particles get caught in magnetic loops, spun faster and faster until they're hurled into the void like cosmic bullets. Others are funneled into narrow beams, their energy concentrated into dazzling displays visible across the electromagnetic spectrum. What's truly mind-bending is how these fields defy our expectations. Near Sagittarius A, magnetic forces don't just assist gravity, they compete with it. In some cases, they even overpower the black hole's pull, redirecting doomed matter into escape routes rather than letting it vanish into oblivion. It's as if the black hole has an invisible hand, deciding which particles get consumed and which get a one-way ticket to intergalactic space. And the effects ripple far beyond the black hole's immediate vicinity. These magnetic highways shape the entire galactic center, influencing star formation, heating interstellar gas, and even regulating how the Milky Way evolves over billions of years. Without them, our galaxy would look utterly different, quieter, dimmer, and far less dynamic. Yet for all their power, these magnetic fields remain elusive. They don't glow or emit sound. We only detect them by observing how they bend light, twist particle paths, or leave imprints on the hot plasma swirling around the black hole. Each new observation peels back another layer, revealing a hidden force that's as essential to the cosmos as gravity itself. And just as enigmatic, one thing's certain: Sagittarius A isn't just a monster. It's an artist painting the galaxy with strokes of magnetism we're only beginning to understand. And with every discovery, we get closer to unraveling one of the universe's most profound secrets: how magnetic fields, invisible yet omnipresent, dictate the fate of everything they touch. These jets of plasma erupting from black holes aren't just random cosmic fireworks, they're precision engineered by some of the most powerful magnetic fields in existence. Take the iconic jet blasting from the supermassive black hole at the heart of galaxy M87, famously imaged by the Event Horizon Telescope. Stretching 5,000 light-years into space, this luminous beam isn't propelled by gravity alone. It's the result of magnetic fields so tightly wound, they function like cosmic particle slingshots, accelerating matter to nearly the speed of light. The secret lies in the black hole's accretion disk, a swirling maelstrom of superheated gas and dust. As this material spirals inward, it doesn't just fall chaotically. Magnetic field lines anchored to the disk get twisted into a colossal helix by the black hole's rotation. Picture a rubber band wound tighter and tighter until it snaps, releasing stored energy. Here, the snap is a magnetic eruption channeling particles into narrow, focused jets along the black hole's rotational axis. The fields act like invisible rails, keeping the jet collimated, so straight and narrow that even across thousands of light years it barely widens. M87's jet offers a stunning case study. Observations reveal its particles are shockingly organized, all moving in sync as if guided by an unseen force. That force is magnetism, creating a feedback loop where the jet's own energy reinforces the fields powering it. At the base of the jet, magnetic coils accelerate electrons to such extreme speeds they emit bright synchrotron radiation, light we can detect from Earth. And sometimes the jet even knots and flickers, betraying violent magnetic reconnections, where field lines break and realign in explosions brighter than a trillion suns. What's even more remarkable is how these magnetic processes mimic technology right here on Earth. Particle accelerators like the Large Hadron Collider use magnetic fields to steer protons at high speeds, just on a vastly smaller scale. Nature's version, however, operates with mind-bending efficiency, turning a black hole's spin into a universal power source. Some theories suggest these jets could be the birthplaces of ultra-high-energy cosmic rays particles that strike Earth's atmosphere with energies far beyond anything our colliders can produce. Yet for all their brilliance, these jets raise profound questions. How do magnetic fields remain so stable over such colossal distances? Why do some black holes produce jets while others, like Sagittarius A star, remain relatively quiet? Each observation peels back another layer, revealing magnetism not just as a side effect of cosmic chaos, but as a master architect shaping the universe in ways we're only beginning to decode. One thing's certain: where black holes and magnetic fields collide, the universe writes its most dramatic physics in the sky. Our sun may seem calm from a distance, but beneath its glowing surface rages a churning ocean of plasma and magnetism, a cosmic engine capable of unleashing storms that could cripple modern civilization. Every 11 years, the sun undergoes a dramatic transformation known as the solar cycle, where its magnetic poles flip like a giant cosmic switch. This isn't just a simple reversal, it's the culmination of a turbulent process driven by the solar dynamo, a self-sustaining generator powered by the sun's rotating plasma. Picture molten metal swirling in Earth's core, but scaled up to stellar proportions, with electrically charged gas twisting magnetic fields into knots of unimaginable energy. Those tangled fields are where the real danger lies. When stressed beyond their limits, they snap like overstretched rubber bands, releasing pent-up energy as solar flares, explosions brighter than 1,000,000 hydrogen bombs. The most violent of these eruptions don't just stop at light. They hurl billion-ton clouds of magnetized plasma, called coronal mass ejections, into space at speeds exceeding 1,000,000 miles per hour. And if one strikes Earth, the results can be catastrophic. History offers a sobering example: the Carrington Event of 1859, named after astronomer Richard Carrington, who witnessed the solar flare that triggered it. This storm unleashed auroras so bright they turned night into day as far south as the Caribbean. Telegraph systems, the cutting-edge technology of the era, sparked and caught fire, with operators reporting shocks and equipment melting mid-transmission. If a similar event occurred today, the consequences would be far more severe. Modern power grids, satellites, and communication networks could face trillions in damages, with blackouts lasting months or even years as transformers fried by geomagnetic currents are painstakingly replaced. Yet the sun's magnetic tantrums aren't purely destructive. They're also a vital reminder of our place in a dynamic solar system. Auroras, those dazzling polar lights, are the benign side of this process: charged particles from solar winds dancing along Earth's magnetic shield. Even the solar cycle itself plays a role in shaping our climate, with some studies suggesting subtle links between periods of low solar activity and regional cooling trends. Understanding this magnetic dance isn't just academic. Space agencies now monitor the sun around the clock, watching for telltale signs of brewing storms. Satellites like NASA's Solar Dynamics Observatory capture intricate details of magnetic field lines writhing across the solar surface, giving scientists precious hours or days to prepare for incoming ejections. Power grid operators drill for space weather emergencies, implementing protocols to isolate vulnerable infrastructure. It's a global effort to guard against a threat that, unlike earthquakes or hurricanes, comes not from within our planet but from the star that gives us life. The sun's dynamo reminds us that magnetism isn't just a curious force. It's the invisible hand shaping everything from the light in our sky to the devices in our pockets. And as we become more technologically dependent, decoding its secrets isn't just about scientific wonder. It's about survival. Those dark blemishes dotting the sun's fiery surface aren't just cosmic freckles, they're windows into the star's restless magnetic soul. Sunspots appear deceptively simple at first glance, dark patches against the solar glow. But peer closer and you'll uncover raging storms of magnetism strong enough to swallow Earth whole. Each one marks a place where the sun's tangled magnetic field erupts through the surface, creating portals where energy builds, twists, and occasionally explodes with devastating consequences. What makes these features so extraordinary is their sheer magnetic might. A typical sunspot's field measures around 2,000 to 4,000 Gauss, roughly 5,000 times stronger than Earth's protective magnetic bubble. That intensity chokes off the normal flow of heat from the sun's interior, cooling the surface enough to make the region appear darker against the surrounding inferno. But don't let their shadowy appearance fool you. This temporary cooling concentrates even more energy beneath the surface, like pressing a thumb over a garden hose. The pressure builds until it finds release in solar flares or coronal mass ejections, those billion-ton tantrums that can wreak havoc across the solar system. Modern telescopes reveal sunspots in jaw-dropping detailed canyons of plasma swirling around their edges, intricate filaments following magnetic field lines like iron filings around a bar magnet. Some display mesmerizing symmetry, with a central dark core called the umbra surrounded by a feathery penumbra where magnetic fields splay outward like the spokes of a wheel. Others grow into sprawling complexes, merging into active regions larger than Jupiter that can unleash X-class flares, the most powerful category of solar explosions. The connection between sunspots and space weather is so fundamental that scientists use them as early warning signs. During periods of peak solar activity, when sunspots multiply across the sun's face like a celestial measles outbreak, the risk of disruptive storms skyrockets. The infamous Halloween storms of 2003 traced back to a cluster of sunspots designated Region 486, which produced 17 major flares in 2 weeks, including the most powerful ever recorded. The resulting auroras dazzled skywatchers as far south as Florida, while radiation bursts forced astronauts on the International Space Station to take shelter and scrambled satellite operations worldwide. Yet for all their destructive potential, sunspots also hold clues to one of solar physics' greatest mysteries, the dynamo process that generates the sun's magnetic field in the first place. By tracking how sunspots migrate across the solar disk and change polarity over 11-year cycles, researchers piece together the complex dance of plasma currents beneath the surface. Some theories suggest deep-seated rivers of electrically charged gas, flowing at different speeds near the sun's poles and equator, stretch and twist magnetic fields until they snap through the surface as sunspots. Others point to instabilities in the tachocline, a turbulent boundary layer between the sun's radiative and convective zones, as the birthplace of these magnetic knots. The more we learn, the stranger these features become. Recent observations show sunspots acting as natural waveguides for solar acoustics, channeling sound waves through the sun's interior like cosmic subway tunnels. Others reveal dark cores within dark cores, Russian doll structures where magnetic fields reach even more extreme concentrations. And then there are the super sunspots, monster active regions like the one responsible for the 2012 near-miss coronal mass ejection that could have plunged modern civilization into a technological dark age had it struck Earth just 1 week earlier. Sunspots serve as both storm warnings and scientific gold mines, their shifting patterns writing the sun's magnetic diary in real time. They remind us that our star isn't a placid ball of light, but a seething, twisting, ever-changing beast, one whose moods, written in magnetism, we're only beginning to translate. Every dark patch tells a story of forces vast beyond comprehension, playing out on a stage where the stakes include the very technology binding our global civilization together. And as telescopes grow sharper and models more sophisticated, each revelation peels back another layer of this ongoing solar drama, one spot at a time. Jupiter doesn't just have a magnetic field, it wields a cosmic force field so vast it could swallow the Sun. At nearly 20,000 times stronger than Earth's, this invisible shield stretches over 4 million miles into space, powerful enough to deflect solar winds that would strip atmospheres from lesser planets. But here's the twist: Jupiter's magnetism isn't a protective bubble. It's a radiation death trap charged with particles accelerated to near light speed, creating the most hostile environment in our solar system outside a black hole. The gas giant's magnetic might comes from its churning interior. Deep beneath those colorful cloud bands, hydrogen gets crushed under such extreme pressure it morphs into metallic liquid, an electrically conductive ocean spinning at dizzying speeds. This swirling metallic hydrogen acts like a planetary-scale dynamo, generating a magnetic field that's not only immensely strong but bizarrely lopsided. NASA Juno spacecraft revealed the field's northern hemisphere is wildly uneven, with patches of intense magnetism clustered like cosmic bruises. Some regions pack triple the strength of others, creating a magnetic fingerprint more chaotic than anything scientists predicted. Nowhere is this chaos more visible than at Jupiter's poles. While Earth's auroras form delicate rings, Jupiter's are continent-sized firestorms, swirling with energies that would vaporize spacecraft in seconds. Juno's close passes captured these light shows in unprecedented detail, electrons screaming along magnetic field lines, colliding with atmospheric gases to unleash ultraviolet storms brighter than entire cities. But the real surprise came when scientists spotted secondary auroras dancing at lower latitudes, fueled by particles stolen from volcanic moon Io. These unexpected displays proved Jupiter's magnetic reach extends far beyond the planet itself, turning its moons into unwitting power sources for its celestial light shows. The radiation trapped in Jupiter's magnetic belts tells an even darker story. Charged particles whip around at relativistic speeds, creating a donut-shaped zone of death called the radiation torus. This is no ordinary hazard, it's a particle accelerator the size of a planet, where electrons reach energies so high they mimic conditions near collapsing stars. Juno's radiation-hardened electronics still took a beating, with each orbit delivering the equivalent of 100 million dental X-rays to its instruments. Without its titanium vault shielding, the probe would have been fried within months. Yet for all its fury, Jupiter's magnetic field plays a cosmic role we're only beginning to appreciate. It acts as a solar system vacuum cleaner, using its immense gravity and magnetism to capture potentially hazardous comets and asteroids. Some researchers believe it may have shielded inner planets like Earth during the solar system's violent early years. Others suggest its radiation belts could hold clues to how particle acceleration works in distant pulsars and quasars. Every new Juno data dump peels back another layer of this magnetic enigma, from the weirdly shallow jet streams that may drive its dynamo to the bizarre blueberry storms spotted near its north pole. One thing's certain, Jupiter's magnetic field isn't just bigger than Earth's. It's an entirely different beast, rewriting the rules of planetary physics with every orbit the plucky little spacecraft completes. And as long as its instruments hold out, we'll keep uncovering secrets about this magnetic giant that challenge everything we thought we knew about how planets work. Saturn's magnetic field shouldn't exist, at least not the way it does. Unlike Jupiter's chaotic, lopsided magnetism or Earth's tilted field, Saturn's is unnervingly precise, aligning almost perfectly with the planet's rotation axis. This near-perfect symmetry defies everything we know about how planetary dynamos work. Normally, magnetic fields get their tilt from the turbulent, uneven churning of conductive fluids inside a planet's core. But Saturn's field is so orderly it's as if the gas giant swallowed a perfectly balanced bar magnet, a cosmic anomaly that's left scientists scratching their heads for decades. The mystery deepens when you peer beneath Saturn's cloud tops. Like Jupiter, the planet's interior is a supercritical soup of metallic hydrogen, spinning at breakneck speeds to generate magnetism. But whereas Jupiter's dynamo roils with asymmetry, its northern and southern hemispheres behaving like mismatched siblings, Saturn's internal engine runs with eerie precision. Data from NASA Cassini spacecraft revealed the field's symmetry extends deep into the planet, suggesting something unusual is stabilizing the chaos. One leading theory points to a hidden layer of helium rain. As helium condenses and falls toward the core, it may smooth out irregularities in the fluid motion, acting like a cosmic shock absorber for the dynamo. Others speculate that Saturn's deep interior contains a stable, conductive shell, perhaps a layer of ionized water or other exotic materials, that filters out turbulence before it reaches the surface. Then there's the enigma of timing. Saturn's magnetic field pulses with a rhythm that matches its rotation period almost exactly, creating a planetary-scale heartbeat we can detect from Earth. This clockwork regularity is bizarre because magnetic fields usually wobble, drift, or even reverse over time. Yet Saturn's ticks along with the stability of an atomic clock, its axis barely deviating by 1/10 of a degree. Some researchers wonder if this precision hints at a core unlike anything else in our solar system, a stratified, onion-like structure where each layer rotates in sync, damping down the chaos that typically twists magnetic fields askew. The implications reach far beyond Saturn. If we can crack how its field stays so perfectly aligned, it could rewrite our understanding of planetary formation. Maybe gas giants elsewhere in the galaxy hide similar magnetic symmetries hidden beneath their swirling atmospheres. Or perhaps Saturn is a cosmic fluke, its unique history of collisions or internal chemistry leaving it with a magnetism that's the exception, not the rule. Every new discovery peels back another layer of this puzzle, proving that even in the well-trodden territory of our solar system, the universe still guards its most elegant secrets. Earth's magnetic field isn't the steadfast guardian we imagine. It's more like a restless sleeper tossing and turning throughout geologic time. Every few 100,000 years, on no set schedule, our planet's magnetic poles swap places in an event called a geomagnetic reversal. North becomes south, south becomes north, and for centuries in between, Earth's protective shield weakens, leaving us more exposed to cosmic radiation and solar storms. The last full reversal happened 780,000 years ago, long before modern humans walked the planet. But the next one could already be underway right now. The magnetic North Pole is sprinting across the Arctic at 55 kilometers per year, while the overall field strength has dropped by 10% over the past 170 years. What causes this planetary identity crisis? Deep beneath our feet, in the outer core's swirling ocean of liquid iron, lies the answer. As molten metal churns around the solid inner core, it generates electric currents that power our magnetic field, a process called the geodynamo. Normally, this system runs smoothly, with convection currents and Earth's rotation keeping the magnetic poles roughly aligned with the geographic ones. But sometimes turbulence wins. Patches of reversed magnetism can emerge in the core, like rebellious territories declaring independence. If enough of these patches merge, they can weaken the dominant field and eventually trigger a full-scale flip. The transition period is where things get messy. During reversals, Earth's field doesn't just neatly invert, it fractures into multiple temporary poles scattered across the globe. Imagine a bar magnet shattered into a dozen pieces, each pointing in random directions. For thousands of years, compass needles wouldn't reliably point north. Navigation systems would falter. More critically, our weakened magnetic shield would let more solar particles slip through, potentially increasing radiation exposure at ground level and wreaking havoc on satellites and power grids. Yet, contrary to doomsday predictions, reversals aren't mass extinction events. Geological records show life carried on through hundreds of past flips. The real danger isn't the reversal itself, it's our modern technological vulnerability. A weaker field during the transition could amplify the damage from solar storms, like the one that nearly missed Earth in 2012. That explosion of plasma from the Sun would have caused widespread blackouts and satellite failures had it arrived just 1 week later. During a reversal, such storms could become more frequent and severe. But here's the twist: we're already overdue for a flip based on the erratic rhythm of past reversals. Sediment cores and lava flows reveal these events happen anywhere from 40,000 to several million years apart, with no predictable pattern. Some reversals take just a few thousand years, others drag on for 20,000. Scientists monitoring today's rapidly shifting field debate whether we're seeing early reversal signals or merely a temporary fluctuation. Satellites like Europe's Swarm mission now track these changes with unprecedented precision, mapping the ebb and flow of our planet's invisible armor in real time. The irony: this looming uncertainty gives us an edge. Unlike our ancestors, we can prepare hardening power grids, improving space weather forecasts, and developing radiation-resistant technology. Earth's magnetic field may be capricious, but human ingenuity, that's one force that never flips. Mars wasn't always the frozen desert we see today billions of years ago. It had rivers, lakes, even a thick atmosphere that could have nurtured life. But there's one critical difference between then and now. Mars lost its magnetic shield, and that single event doomed the planet's chances of staying habitable. Unlike Earth, where our magnetic field deflects solar winds and preserves our atmosphere, Mars' protective bubble collapsed long ago, leaving it vulnerable to the relentless stripping by charged particles from the Sun. The result: an atmosphere so thin it's just 1% the density of Earth's, and a surface so irradiated nothing survives unprotected. The mystery of Mars' missing magnetism begins deep beneath its rusty surface. Evidence from spacecraft like MAVEN and Mars Global Surveyor reveals something startling: ancient volcanic rocks are magnetized in strange, alternating bands, suggesting Mars once had a planetary-scale magnetic field similar to Earth. These magnetic fossils, locked in the crust for over 4 billion years, tell a story of a molten core that once churned with enough energy to power a global dynamo. But then, for reasons still debated, that dynamo sputtered and died. Some theories point to Mars' smaller size. Its core cooled faster than Earth's, solidifying just enough to shut down the convective currents needed to sustain a magnetic field. Others suggest a catastrophic impact, like the one that carved out the enormous Borealis basin, may have disrupted the core's dynamics beyond recovery. Whatever the cause, the aftermath was brutal. Without a magnetic shield, solar wind streams of charged particles racing from the Sun at 1 million miles per hour began eroding Mars' atmosphere molecule by molecule. MAVEN measurements show this stripping still happens today, with oxygen and carbon dioxide ions ripped away by the Sun's magnetic tendrils at a rate of about 100 grams every second. Over billions of years, that adds up. Models suggest Mars may have lost enough atmosphere to cover the planet in a layer 20 feet deep, enough to maintain liquid water and possibly even support microbial life before the Great Drying began. This raises a haunting question. Did life ever gain a foothold before the field collapsed? The most promising places to look are underground, where geothermal heat and shielding from radiation could have sustained microbes long after the surface became inhospitable. Future missions like NASA's Perseverance rover searching for fossilized microbial mats, or ESA's Rosalind Franklin rover drilling for subsurface organics, aim to find out. But even if life existed, its fate was sealed the moment Mars' core stopped spinning its magnetic shield. For future colonists, this presents both a challenge and an opportunity. Without a natural magnetic field, any attempt to terraform Mars would require artificial solutions, ideas ranging from orbiting magnetic deflectors to reigniting the core through nuclear detonations, though the latter remains firmly in science fiction territory. More realistically, habitats would need heavy radiation shielding, possibly built from Martian regolith, while agriculture might rely on underground hydroponic farms bathed in artificial light. Some scientists propose creating localized magnetic bubbles around key settlements, miniature versions of Earth's magnetosphere just strong enough to deflect the worst solar winds. Mars stands as a stark warning of how fragile planetary habitability can be. Its story hints at a narrow window where size, distance from the Sun, and geological luck align to sustain a protective magnetic cocoon factors that lined up perfectly for Earth but failed Mars in the end. As we search for life beyond our solar system, this lesson looms large. A planet's magnetic field might be just as crucial to its survival as liquid water or a stable climate. And for our own world, it's a reminder of the invisible force field we too often take for granted, one that, if lost, could rewrite our future as dramatically as it did Mars' past. Venus should have a magnetic field. By all cosmic logic, this hellish world, often called Earth's twin, possesses everything needed to generate one. A massive iron core, a molten interior, and enough internal heat to keep its engine running. Yet spacecraft measurements confirm the shocking truth: Venus has no global magnetic field to speak of. It's a planetary anomaly that defies expectations, leaving scientists scrambling to explain how a world so similar to ours could lack this fundamental shield against solar radiation. The mystery begins with Venus' sluggish spin. While Earth completes a rotation every 24 hours, Venus takes 243 Earth days longer than its own year. This glacial pace might be the key to its magnetic silence. Planetary dynamos rely on the Coriolis effect, the same force that shapes hurricanes, to twist conductive fluids into organized patterns. Earth's rapid rotation keeps its liquid iron outer core churning in structured convection currents, generating a stable magnetic field. Venus, by contrast, spins so slowly that its core may resemble a pot of barely simmering soup, too sluggish to produce large-scale magnetic organization. Some models suggest its molten iron simply sloshes chaotically rather than forming the orderly currents needed to sustain a dynamo. But rotation speed alone doesn't solve the puzzle. Mars spins nearly as fast as Earth, yet lost its magnetic field billions of years ago, while Mercury, with a day lasting 59 Earth days, somehow maintains a weak but detectable field. This forces scientists to consider another piece of Venus' peculiar physics: its lack of plate tectonics. On Earth, the constant recycling of crustal plates helps regulate internal temperatures, possibly stabilizing core convection. Venus' stagnant lid crust traps heat unevenly, potentially creating pockets of superheated core material that disrupt coherent fluid motion. Without the thermal blanket of plate tectonics, Venus' core might cool in fits and starts, preventing the sustained dynamo action needed for a global field. Then there's the question of composition. Recent simulations propose that Venus' core could contain lighter elements like oxygen or sulfur mixed with iron, impurities that might alter its conductivity. Earth's core is predominantly iron-nickel, an ideal mix for efficient dynamo generation. If Venus' core is contaminated with other materials, its ability to generate magnetic fields could be smothered at the source. Some researchers even speculate that Venus' core might be partially crystallizing, forming a solid inner core like Earth's, but in a lopsided, asymmetric way that stifles magnetic coherence. The consequences of this magnetic absence are written across Venus' desolate landscape. Without protection, solar winds have battered its atmosphere for eons, stripping away hydrogen and leaving behind a suffocating blanket of carbon dioxide. The runaway greenhouse effect that followed turned the planet into a 700-degree furnace with surface pressures 90 times Earth's. Yet paradoxically, Venus' thick atmosphere has become a temporary shield, so dense that it slows atmospheric erosion, buying time for scientists to study how a planet without magnetism copes with the violence of space. Probes like ESA's Venus Express and Japan's Akatsuki have detected weak, patchy magnetic fields induced by the solar wind's interaction with the upper atmosphere, ghostly echoes of what might have been. These flickering remnants hint that Venus' story isn't over. Some theories suggest the planet undergoes sporadic magnetic rebirths during periods of intense volcanic activity, when massive lava flows temporarily redistribute internal heat and kickstart limited dynamo action. If true, Venus could be a planet stuck in magnetic hibernation, waiting for the next geologic wake-up call. Understanding Venus' magnetic silence isn't just academic, it's a window into planetary evolution. As we discover thousands of exoplanets, many likely resemble Venus in size and composition. Knowing why some worlds retain protective magnetic fields while others lose them could redefine our search for habitable worlds. Venus stands as a cautionary tale. Even twin planets can meet vastly different fates, shaped by the invisible currents churning or failing to churn beneath their surfaces. Mercury shouldn't have a magnetic field, at least that's what scientists assumed for decades. The smallest planet in our solar system, barely larger than Earth's moon, was thought to have cooled off long ago, its core solid, its dynamo silent. Yet when NASA, a messenger spacecraft, entered Mercury's orbit in 2011, it uncovered a startling truth. This tiny world hums with a faint but unmistakable magnetic field, 1% the strength of Earth's. This discovery rewrote the textbooks, forcing a radical rethink of how even the smallest planets can generate cosmic magnetism. The secret lies in Mercury's partially molten core. Unlike Mars, whose dynamo died as its core froze, Mercury's heart remains surprisingly lively. Messenger-precise gravity measurements revealed a core so massive it occupies nearly 85% of the planet's radius, a proportion unmatched in the solar system. Within this oversized core, a molten outer layer sloshes around a solid inner core, creating just enough motion to sustain a weak magnetic field. It's like a dying campfire that, against all odds, still emits faint embers. The puzzle: Mercury's core should have cooled completely billions of years ago. One theory suggests sulfur mixed with the iron lowered its melting point, keeping it liquid far longer than expected. Another proposes that tidal forces from the sun's gravity flex the planet's interior, generating enough heat to stave off total solidification. But Mercury's magnetism isn't just a curiosity, it's a cosmic battleground. Solar winds, unimpeded by any substantial atmosphere, batter the field into a lopsided shape, compressing it on the sunward side while stretching it into a long tail behind the planet. Messenger spotted bizarre twists in this tail, where magnetic field lines snap and reconnect, unleashing bursts of energy that hurl charged particles toward Mercury's surface. These events, similar to Earth's aurora producing substorms but on a far smaller scale, etch the planet's rocky face with strange, swirling patterns of discoloration. The implications stretch far beyond our solar system. If a planet as small and sun-scorched as Mercury can cling to a magnetic field, then exoplanets we once dismissed as too tiny or too close to their stars might still harbor protective shields, and with them the potential for atmospheres or even life. Mercury's faint hum of magnetism whispers a tantalizing possibility that the universe might be far more hospitable than we ever imagined, one magnetic flicker at a time. Pulsars don't just spin, they scream into the void with lighthouse precision, their beams slicing through space like cosmic searchlights. What guides these perfectly timed pulses isn't just gravity or rotation, but some of the most intense magnetic fields in the universe. Picture a neutron star, the collapsed core of a dead star, spinning hundreds of times per second. As it whirls, its magnetic field trillions of times stronger than Earth's, channels radiation into narrow beams shooting from its poles. When these beams sweep across Earth, we detect them as rhythmic pulses, so regular they rival atomic clocks in accuracy. The discovery of these celestial metronomes is a story of scientific serendipity. In 1967, Cambridge researcher Jocelyn Bell noticed an odd signal in her radio telescope data, a series of pulses spaced precisely 1.3 seconds apart. The pattern was so artificial searching, her team labeled it LGM for Little Green Men, briefly entertaining the wild possibility of extraterrestrial contact. But as more pulsars were found, the truth became clear. These weren't alien broadcasts, but the signatures of rapidly spinning neutron stars, their magnetic fields acting like cosmic amplifiers for their beams. What makes pulsars truly astonishing is how their magnetism shapes their signals. The beams aren't random, they follow the star's magnetic axis, which often tilts away from its rotational axis. This misalignment creates the lighthouse effect as the beams sweep past our line of sight with each rotation. Some pulsars, like the famous Crab pulsar, even whip their beams around so fast they flash 30 times per second, visible across multiple wavelengths from radio to gamma rays. The Crab's magnetic field, though a mere trillion times Earth's, accelerates particles to near light speed, generating secondary shockwaves that glow in sync with the pulses. Yet pulsars are more than just cosmic timekeepers. Their magnetic fields are so powerful they distort space-time around them, creating detectable ripples in the fabric of the universe. The fastest spinning pulsars, called millisecond pulsars, are so stable their timing can reveal gravitational waves passing through our galaxy, subtle stretches and compressions in space itself. Others, like the binary pulsar PSRB 1913+16, provided the first indirect evidence for gravitational waves, earning its discoverers a Nobel Prize. The legacy of that first misunderstood signal, LGM1, lives on in every pulsar study since. These magnetic lighthouses have become universal tools, helping us map the Milky Way structure, test Einstein's theories, and even navigate spacecraft. Some researchers propose using pulsar beams as interstellar GPS, their predictable pulses guiding future voyages beyond our solar system. From false alarms about aliens to cornerstone discoveries in astrophysics, pulsars remind us that the universe's most precise phenomena often arise from its most extreme forces, where magnetism doesn't just shape stars, but helps us decode the cosmos itself. Before a star ignites its nuclear furnace, it feeds on chaos, a swirling disk of gas and dust spiraling inward in a cosmic dance. But hidden in that chaos is an invisible conductor, magnetic fields threading through the protostellar disk like cosmic puppet strings. These fields don't just watch the show, they orchestrate it, channeling material onto the growing star with eerie precision. Recent images from the ALMA telescope reveal these structures in stunning detail, showing filaments of dust and gas aligned along magnetic field lines like iron filings around a magnet. What looks like random turbulence is actually a highly organized delivery system, where magnetism guides the birth of stars. The process starts with a collapsing molecular cloud, where gravity pulls material inward while rotation flattens it into a disk. Without magnetic fields, this disk would spin itself apart, flinging material into space before the star could grow. But magnetism solves the problem elegantly. As charged particles move through the disk, they generate electric currents, which in turn create magnetic fields that twist and braid around the young star. These fields act like cosmic conveyor belts, transporting material inward while shedding excess angular momentum outward. ULMA observations of protostar IRS 1628-2215 even show spiral arms in the disk, dense ridges where magnetic forces have concentrated material, funneling it toward the hungry protostar at the center. The real magic happens at the disk's inner edge, where magnetic fields become so intense they launch jets of material perpendicular to the disk. These bipolar jets, visible in ULMA radio images as glowing towers of plasma, are nature's way of balancing the books, ejecting excess energy and momentum so the star can keep growing. The fields accelerate particles to nearly light speed, creating streams that stretch light years into space. Some jets even exhibit knots and shocks, evidence of episodic outbursts where the star gorges on sudden influxes of magnetically delivered material. What's most remarkable is how these processes scale. Whether it's a modest star like our Sun or a massive stellar behemoth, the same magnetic choreography plays out, just with higher stakes. In disks around massive protostars, magnetic fields are so strong they can tear gas clouds into ribbons, creating intricate webs of filamentary structures. ULMA view of ORIK reveals such a web, with dust grains aligned like compass needles along field lines, tracing patterns that resemble celestial spider silk. These filaments aren't just pretty, they're highways for material, ensuring even the most massive stars get fed efficiently. Yet mysteries remain. Some disks show magnetic fields that defy expectations, twisting into hourglass shapes or even reversing polarity. Others seem to lack strong fields entirely, suggesting alternative mechanisms might sometimes dominate. Each new ULMA image adds pieces to the puzzle, revealing how universal and how versatile magnetic fields are in shaping stellar nurseries. One thing's certain, without these invisible architects, the universe would be a far darker place, its stars stillborn in clouds of unorganized chaos. Gravity may pull the cosmic gas and dust together, but magnetic fields decide how that material ultimately forms a star. These invisible forces act as cosmic referees, stepping in when gravity gets too greedy, slowing collapse just enough to prevent chaotic, runaway star formation. This delicate balancing act starts in the cold, dark molecular clouds where stars are born. As gravity begins compressing these clouds, their embedded magnetic fields push back, creating a tug-of-war that shapes stellar nurseries across the universe. Observations of young protostars reveal this magnetic resistance in action. Gas doesn't simply free fall inward, it spirals gradually along magnetic field lines like beads on a twisted wire. This process, called magnetic braking, works similarly to a bicycle dynamo. As charged particles move through the field, they generate electric currents that sap rotational energy. Without this braking effect, spinning gas clouds would fling themselves apart before stars could form. The Orion Nebula offers a stunning case study, where astronomers have mapped magnetic fields threading through star-forming filaments, their tension visibly slowing material's inward rush. The numbers behind this phenomenon are staggering. In some dense cloud cores, magnetic pressure can support regions against gravity's pull, even when outward forces outweigh inward mass by 10-to-1, like a balloon resisting a crushing grip. Only when enough material accumulates to overwhelm this magnetic support does collapse proceed. Even then, fields continue guiding the process, funneling gas into flattened disks where fledgling stars can feed efficiently. Yet magnetic braking isn't perfect. Some material inevitably escapes this orderly transfer, ejected in spectacular jets that shoot from the star's poles at hundreds of kilometers per second. These outflows act as cosmic pressure valves, carrying away excess angular momentum that would otherwise prevent the star from growing. The result is a star born not from chaos, but from magnetic choreography, a dance where fields and gravity find equilibrium, one stellar nursery at a time. The Milky Way isn't just a scatter of stars, it's threaded with invisible magnetic highways, vast filaments stretching tens of thousands of light years that weave through our galaxy like cosmic stitching. These colossal structures, far from static, pulse with energy, channeling particles and sculpting clouds of gas into the raw materials for new stars. Unlike the violent fields around magnetars or black holes, galactic magnetism works on an unimaginably grand scale, its influence felt across entire spiral arms. We can't see these fields directly, but starlight holds the key. As light travels through space, passing through regions with magnetic fields, its waves become polarized, aligned in specific orientations. Telescopes like Planck and Sophia have mapped this polarization across the Milky Way, revealing intricate patterns where dust grains, shaped by magnetism, act like tiny compass needles. The resulting images show a galaxy crisscrossed with magnetic threads, some following spiral arms, others twisting into unexpected knots and loops. One particularly striking filament near the galactic center, dubbed the Magnetic Tower, stretches over 600 light-years vertically, its field lines so orderly they resemble the grooves on a vinyl record. These fields don't just decorate space, they govern it. Cosmic rays, those high-energy particles racing through the galaxy at nearly light speed, don't travel randomly. They surf along magnetic field lines like cars on a roller coaster, their paths bending around these invisible rails. This explains why certain regions of the galaxy, like the Cygnus X star-forming complex, blaze with unusually intense cosmic ray activity. Their tangled magnetic webs act as natural particle accelerators. Even more remarkably, these fields shape the very clouds where stars are born. In the Taurus molecular cloud, magnetic pressure fights gravity's pull, preventing some gas clumps from collapsing while channeling others into slender, star-forming filaments. The origin of these galaxy-spanning fields remains one of astrophysics' great puzzles. Some theories suggest they're primordial, dating back to the universe's infancy when quantum fluctuations imprinted magnetic seeds later amplified by galactic rotation. Others propose they're continually regenerated by turbulent gas motions and stellar explosions, like a cosmic dynamo running on supernova. Whatever their source, their impact is undeniable. Without these invisible scaffolds, our galaxy would lack the structure needed to birth stars, planets, and ultimately, life itself. Recent studies have even hinted that galactic magnetism might reach beyond individual galaxies, connecting clusters in a vast cosmic web of magnetized filaments, an idea that, if confirmed, would redefine our understanding of how the universe organizes itself on the largest scales. For now, each new polarization map peels back another layer of this magnetic tapestry, revealing a Milky Way far more intricate and dynamic than we ever imagined. The Andromeda Galaxy might be our closest cosmic neighbor, but its magnetic personality couldn't be more different from the Milky Way's. While our galaxy's magnetic fields stretch in elegant spirals, tracing the arms like invisible ink, Andromeda's magnetism is a chaotic web, patchy, turbulent, and oddly concentrated in its outer reaches. Recent radio telescope observations reveal this stark contrast, painting a portrait of two galaxies that, despite their similar size and shape, have taken wildly divergent magnetic paths. What makes Andromeda's magnetic field so puzzling is how it defies expectations. Using the Effelsberg radio telescope in Germany, astronomers mapped its polarization patterns, expecting to find the same orderly spiral structure seen in the Milky Way. Instead, they discovered a field strongest not along the arms, but in the faint halo of gas surrounding the galaxy's disk. This outer field isn't just strong, it's twisted into bizarre loops and knots, as if the galaxy's magnetism had been stirred by some unseen cosmic hand. Some regions show fields aligned with Andromeda's rotation, while others stubbornly oppose it, creating a magnetic tug of war on an interstellar scale. The differences may hold clues to how galaxies age. The Milky Way's magnetic field is thought to be powered by a dynamo effect, its rotation twisting and amplifying magnetic lines over billions of years. But Andromeda's messy field suggests its dynamo might be broken or perhaps never fully formed. One theory points to its violent past. Andromeda has cannibalized smaller galaxies, and each collision could have scrambled its magnetic structure like a spoon through soup. Another idea proposes that its outer halo is a relic from an earlier cosmic era, when galaxies were first assembling and magnetism was imprinted directly from the primordial universe. Radio emissions add another layer of intrigue. In the Milky Way, cosmic rays and magnetic fields work in tandem to produce the synchrotron radiation we detect. Andromeda, however, shows unexpected holes in this emission, vast regions where the radio glow abruptly dims, as if someone had flipped a switch. These could be zones where magnetic fields have been torn apart by turbulence, or where cosmic rays have leaked away through invisible gaps in the galactic magnetic shield. The stakes of this mystery go beyond Andromeda. If two seemingly identical spiral galaxies can develop such different magnetic fingerprints, it forces us to rethink how universal the rules of galactic evolution truly are. Future telescopes like the Square Kilometre Array aim to map these fields in even finer detail, potentially revealing whether Andromeda's chaos is an outlier or a mirror showing our own galaxy's future. After all, in 4 billion years, when the Milky Way and Andromeda collide, their magnetic fields will merge too, weaving a new cosmic tapestry none of our models can yet predict. Long before galaxies spiraled into existence in the universe's first searing moments, magnetic fields may have already been weaving their invisible threads through the primordial chaos. The question of where cosmic magnetism began is one of astrophysics' deepest puzzles. Did it emerge gradually as stars and galaxies formed, or was it imprinted into the fabric of space-time itself during the Big Bang's explosive birth? Recent discoveries suggest the answer lies in the latter, with clues hidden in the faint whispers of the infant universe. Picture the cosmos just microseconds old, a superheated soup of quarks and gluons swirling in a plasma so dense light couldn't escape. Within this cauldron, quantum fluctuations, tiny ripples in the energy field, may have generated the first magnetic seeds. As the universe expanded and cooled, these weak fields could have been amplified by turbulent motions in the plasma, like a spoon stirring cream into coffee. Some theories propose that phase transitions in the early universe, moments when fundamental forces separated from one another, created shock waves that further stretched and twisted these fields. The result, a cosmic tapestry of magnetism, fragile but pervasive, woven into the universe's very structure. The evidence for this primordial origin comes from surprising places. Measurements of distant galaxy clusters reveal magnetic fields even in regions seemingly untouched by stars or supernova, places where magnetism shouldn't exist if it required stellar processes to create it. Even more telling are observations of the cosmic microwave background, the afterglow of the Big Bang. While no direct imprint of primordial fields has been detected yet, subtle patterns in this radiation hint at their possible influence, like faint fingerprints on the universe's oldest photograph. One compelling idea suggests these early fields acted as scaffolding for galaxy formation. Computer simulations show that weak primordial magnetic fields could have guided the collapse of gas clouds in the young universe, channeling material into the filaments and nodes that later birthed the first stars. Without this subtle guidance, galaxies might have formed more chaotically, lacking the elegant spiral structures we see today. It's a cosmic case of nurture over nature, the universe's magnetic midwife quietly shaping its future evolution. Yet mysteries remain. If these fields originated in the Big Bang, why are they so weak today? Some theories point to cosmic inflation, the universe's rapid early expansion, as the culprit. stretching primordial fields until they became nearly imperceptible, like fading ink on an expanding balloon. Others speculate that turbulent plasma motions in the first galaxies amplified these weak seeds, jump-starting the stronger fields we observe now. The search for answers continues, with next-generation telescopes designed to detect the faintest magnetic whispers from the universe's dawn. What's clear is that magnetism isn't just a side effect of cosmic evolution. It may have been a foundational force, as essential to shaping the universe as gravity itself. From the first flickering fields in the primordial plasma to the vast magnetic highways of modern galaxies, this invisible hand has guided the cosmos since the beginning. And as we peel back the layers of time, each discovery brings us closer to understanding how magnetism wrote its silent signature across the stars. Somewhere in the vast expanse of space, atomic nuclei are being hurled across the universe at nearly the speed of light. Particles so energetic they carry the punch of a fastball crammed into a single proton. These are ultra-high-energy cosmic rays, nature's most powerful particle accelerators, and they're surfing an invisible highway of galactic magnetic fields to reach us. Unlike the tidy paths of light, these charged particles don't travel in straight lines. They spiral along magnetic field lines like electrons in a cathode ray tube, twisted and redirected by every magnetic knot and bend they encounter along their multimillion-year journeys. When one finally strikes Earth's atmosphere, it triggers a fireworks show of secondary particles, an air shower so vast it can spread across 40 square kilometers by the time it reaches the ground. Catching these rare, high-energy messengers is the mission of the Pierre Auger Observatory in Argentina, a sprawling detector covering 3,000 square kilometers of Patagonian desert. Its 1,600 water tanks act like cosmic rain gauges, waiting for the telltale blue flash of Cherenkov radiation as air shower particles zip through them faster than light moves in water. Meanwhile, fluorescence telescopes peer upward, tracing the ultraviolet glow of nitrogen molecules excited by the shower's passage. By stitching together these signals, scientists can reconstruct the original cosmic ray's energy and rough direction, though its exact source remains maddeningly elusive. Here's why. Imagine trying to trace the origin of a bullet fired into a hurricane. Galactic magnetic fields, though weak by cosmic standards, are so vast they can deflect a high-energy proton by 30 degrees or more over long distances. The highest energy cosmic rays, dubbed "Oh my God" particles, after one detected in 1991 with the energy of a tennis serve, might originate in active galactic nuclei or colliding galaxy clusters. But by the time they reach us, their paths are so scrambled they point back to empty sky. Auger's data reveals another clue. These ultra-high-energy rays aren't arriving uniformly. They cluster toward nearby galaxies with active cores, suggesting monstrous black holes may be the cosmic railguns firing them our way. Yet the real magic lies in how these particles interact with the galaxy's magnetic scaffolding. Lower energy cosmic rays, the kind raining down constantly, get so tangled in magnetic fields that they effectively lose all memory of their origins, creating a diffuse glow across the sky. But the most energetic ones punch through with enough force that their deflections leave subtle fingerprints in their arrival directions. Auger's latest maps show tantalizing hints of hotspots, places where multiple ultra-high-energy rays seem to whisper, "Look this way." Follow their gaze and you'll find Centaurus A, a gargantuan elliptical galaxy with a jet-spewing supermassive black hole, one of the prime suspects in this cosmic whodunit. What's at stake goes beyond astrophysical curiosity. If we can pinpoint these accelerators, we'll unlock secrets about how black holes channel energy into particles, how magnetic fields structure the cosmos, and perhaps even how the most extreme environments in the universe operate. Every time a cosmic ray slams into Auger's detectors, It's not just a particle hitting the ground, it's a postcard from a magnetic odyssey spanning millions of light years, stamped with clues about the invisible forces shaping our galaxy. And with upgrades underway to Auger's surface and fluorescence detectors, each new data point brings us closer to reading the full message. Magnetic reconnection might sound like a dry physics term, but it's actually one of the most violent and transformative processes in the universe, a cosmic short circuit that unleashes staggering amounts of energy in mere seconds. Picture two rubber bands stretched to their limits, suddenly snapping and whipping back with a burst of stored energy. Now replace those rubber bands with magnetic field lines in space plasma, and you've got the essence of reconnection. This explosive realignment of magnetic fields occurs when oppositely directed field lines collide, break apart, and then reconnect in a new configuration, releasing enough energy to power everything from dazzling auroras to solar storms that can cripple satellites. NASA's Magnetospheric Multiscale Mission, or MMS, has given us front-row seats to this phenomenon. Flying in a tight tetrahedral formation through Earth's magnetosphere, MMS's 4 spacecraft captured reconnection events in unprecedented detail, down to fractions of a second. The data reveals magnetic field lines twisting like writhing snakes before suddenly snapping, accelerating particles to nearly light speed in the process. These observations solved a decades-old puzzle: why reconnection happens far faster than classical physics predicts. The answer lies in electrons breaking free from the plasma's grip, creating microscopic turbulence that turbocharges the entire event. Solar flares offer the most dramatic demonstrations of reconnection's power. In the sun's corona, tangled magnetic loops store energy like compressed springs. When reconnection triggers, it can unleash the equivalent of 10 million hydrogen bombs in minutes, heating plasma to tens of millions of degrees and hurling it across the solar system. The 2017 solar flare observed by NASA SDO showcased this beautifully, field lines erupting in an X-class explosion, their reconnection points glowing white-hot in ultraviolet images. But reconnection isn't just destructive, it's also the engine behind Earth's auroras, those shimmering curtains of light near the poles. When solar wind particles encounter Earth's magnetosphere, reconnection events funnel them along field lines toward the poles, where they collide with atmospheric gases to create the northern and southern lights. Norway's winter skies regularly dance with these displays, their colors reflecting the altitude and type of gas involved: oxygen glowing green or red, nitrogen adding blue or purple hues. The universality of reconnection is what makes it so fascinating. The same process that brightens our skies with auroras also powers gamma-ray bursts from distant galaxies and drives plasma jets from black holes. Laboratories on Earth, like the Princeton Plasma Physics Lab, even mimic reconnection in miniature, hoping to harness its principles for fusion energy. Yet for all our progress, key mysteries remain, like why some reconnection events spark massive eruptions while others fizzle quietly. Every new observation peels back another layer, revealing magnetism's hidden role as both cosmic architect and demolitions expert. Whether sculpting auroras or detonating solar storms, reconnection proves that even the universe's most invisible forces can rewrite reality in the blink of an eye. Auroras aren't exclusive to Earth, they're a universal light show, painted across the skies of worlds with magnetic personalities. But while our northern and southern lights shimmer in delicate greens and purples, other planets host auroras that redefine extreme. Jupiter's polar displays don't just glow in visible light, they scream in X-rays, unleashing bursts of high-energy radiation powerful enough to rival a medical imaging machine. The Hubble Space Telescope and NASA Chandra X-ray Observatory have captured these eerie emissions, revealing pulses that sync with Jupiter's rapid 10-hour rotation. Unlike Earth's auroras fueled by solar wind particles, Jupiter's X-ray storms draw energy from its own volcanic moon Io, whose sulfurous eruptions inject charged particles into the gas giant's magnetic grasp. The result, auroras so vast they could swallow Earth whole, dancing to the rhythm of a moon 350,000 miles away. Saturn takes celestial light shows to another level of strangeness. At its north pole, the auroras don't just shimmer, they're imprisoned within a perfect hexagon of clouds, a six-sided jet stream wider than two Earths. NASA Cassini spacecraft spotted ultraviolet auroras curling along the hexagon's edges, their glow tracing the bizarre geometric boundary like neon paint. What makes this spectacle even more surreal is how Saturn's magnetic field uniquely aligned with its rotation axis funnels particles directly to the poles without the wobble seen on other planets. The hexagon's razor-sharp edges may stem from deep atmospheric waves interacting with these precision-guided magnetic currents, creating a celestial snowflake that's endured for decades. Yet across these radically different worlds, one force orchestrates the spectacle: magnetism. Whether it's Earth's protective shield guiding solar wind particles to the poles, Jupiter's particle slingshot field accelerating ions to X-ray energies, or Saturn's symmetrical funnel concentrating auroras into geometric perfection, magnetic fields are the unseen conductors of the cosmos' greatest light shows. Even frigid Uranus and Neptune, with their off-kilter magnetic axes, host faint auroras that flicker in the solar wind, proof that wherever a planet hides a magnetic heartbeat, the universe finds a way to make it glow. The diversity of these displays isn't just beautiful, it's a scientific goldmine. By comparing planetary auroras, researchers decode the hidden workings of magnetic fields across the solar system. Jupiter's X-rays reveal how magnetic forces can accelerate particles to extreme energies without solar input. Saturn's hexagon showcases how atmospheric dynamics and magnetism intertwine. And Earth's relatively gentle auroras serve as a baseline, illustrating how a planet's atmosphere and magnetic personality shape the final masterpiece. Together, they paint a universal truth: magnetism doesn't just protect worlds, it turns them into canvases where physics becomes art. Earth's magnetic field doesn't just protect us, it imprisons danger in two donut-shaped zones of radiation called the Van Allen belts. These invisible traps, stretching from roughly 1,000 to 60,000 kilometers above our planet, are cosmic containment units where Earth's magnetism corrals charged particles like a celestial spiderweb. Solar wind electrons and protons get caught in this magnetic maze, spiraling wildly along field lines while bouncing between the poles in milliseconds. The result, a radioactive prison so intense it would fry unshielded satellites and prove lethal to astronauts within hours. What makes these belts fascinating is their dynamic nature. The inner belt, packed with high-energy protons, remains relatively stable, a leftover from Earth's encounter with cosmic rays. But the outer belt swells and shrinks like a living organism, its electron population surging during solar storms as if the sun itself were pumping particles into this cosmic holding cell. NASA twin Van Allen probes, launched in 2012, caught these changes in action, revealing how magnetic storms can compress the belts inward or even split the outer belt into three distinct rings temporarily. One particularly violent solar storm in 2015 carved a nearly radiation-free buffer zone between the belts, an atmospheric scar that took months to heal. Then came an unexpected twist in 2017 when SpaceX inadvertently created an artificial radiation belt. During a Falcon 9 launch, the rocket's second stage experienced an anomaly, leaving its payload, a classified government satellite, in too low an orbit. As the stage's fuel tank ruptured, it released enough high-energy electrons to form a temporary third belt between the natural Van Allen zones. For weeks, this man-made radiation shell persisted, visible to satellites as an eerie glow of trapped particles before gradually dissipating. Scientists realized with dismay that a single rocket mishap had altered Earth's magnetic environment, raising sobering questions about how future space traffic might unintentionally reshape our planet's protective systems. The Van Allen belts aren't just obstacles to overcome, they're natural laboratories. By studying how particles behave in these zones, scientists unravel secrets about plasma physics that apply everywhere from nuclear fusion reactors to distant pulsars. The belts also serve as Earth's first line of defense against solar storms, their magnetic walls absorbing and redistributing incoming radiation like a buffer zone. During extreme space weather events, the outer belt balloons outward, sacrificing itself to shield the planet below, a magnetic martyr absorbing the brunt of the sun's fury. Future missions aim to probe these belts further, unlocking their potential as particle accelerators and early warning systems. But their message is clear: Earth's magnetic field isn't just an invisible blanket. It's an active, evolving shield, one that sometimes fights its battles in ways we're only beginning to understand, high above the atmosphere where magnetism writes the rules of engagement. HD 209458b isn't just another hot Jupiter. It's a magnetic maverick bending the rules of planetary physics with a magnetic field that refuses to play nice. This gas giant orbits so close to its star that its atmosphere is literally boiling away, forming a comet-like tail of ionized gas. But here's the twist: instead of being blown into space haphazardly, the escaping particles spiral along precise arcs, betraying the presence of a magnetic field at least 10% as strong as Jupiter's. That's enough force to sculpt stellar winds into submission, creating a magnetosphere visible from 50 light-years away. What makes this discovery revolutionary is how it flips the script on star-planet relationships. Most exoplanets are considered passive victims of their host star's fury, but worlds like HD 209458b fight back. Their magnetic fields don't just deflect stellar winds, they distort the star's own outer atmosphere, creating ripples in the corona that telescopes can detect as subtle X-ray fluctuations. Imagine a planet so magnetically brazen it makes its star flinch. The implications for ultramagnetic hot Jupiters are staggering. Some models suggest these planets could generate fields through tidal heating, their cores stretched and squeezed by gravitational forces until they churn like cosmic dynamos. Others propose that rapid rotation, fueled by their blistering orbits, supercharges their magnetic engines. The result: magnetic behemoths capable of carving cavities in stellar winds, shielding their evaporating atmospheres like force fields. But the real cosmic drama unfolds when these magnetic titans interact with their stars. In extreme cases, a planet's field might channel charged particles back toward the star, sparking auroras on the stellar surface, a reverse version of Earth's northern lights. Some astronomers even speculate that particularly strong planetary fields could induce starspots or alter stellar rotation over time, effectively making the tail wag the dog in these binary systems. This magnetic tug-of-war offers more than just spectacle. It's a lifeline for hypothetical moons. A robust planetary magnetosphere could shield orbiting satellites from lethal stellar radiation, expanding the habitable zone's boundaries inward. Suddenly, hellish worlds closer to their stars than Mercury might harbor habitable oases in their moon's skies, all thanks to magnetic armor we're only beginning to understand. Every new observation peels back another layer of this magnetic mystery, proving that when it comes to extreme exoplanets, the universe's rulebook is still being written in invisible ink. On August 17, 2017, the universe handed scientists a gift wrapped in gravity and fire: GW170817, the first neutron star collision ever witnessed by humanity. This wasn't just a cosmic spectacle, it was a magnetic apocalypse. When these two ultra-dense corpses spiraled into each other at 1/3 the speed of light, their merger didn't just create gravitational waves, it forged a magnetic monster. The moment of impact unleashed a kilonova, an explosion 1,000 times brighter than a typical nova. But what made this event revolutionary was the hidden role of magnetism. As the neutron stars shredded each other, their combined magnetic fields, already billions of times stronger than Earth's, got twisted into a hypercharged vortex. Matter wasn't just ejected, it was catapulted in precise jets, sculpted by magnetic forces so intense they could redirect entire streams of plasma like cosmic traffic cops. Telescopes caught the aftermath in gamma rays, X-rays, and even visible light, while gravitational wave detectors felt the space-time ripples, a triumph of multi-messenger astronomy. But the real breakthrough came from the debris. The collision forged heavy elements like gold and platinum in its magnetic crucible, solving a long-standing mystery about the universe's jewelry box. Spectroscopic analysis revealed these elements weren't scattered randomly. They followed patterns shaped by the merger's magnetic turbulence. Without those fields, the cosmic gold rush might never have reached our solar system. Perhaps most startling was the magnetic aftermath. The remnant, likely a hypermassive neutron star before collapsing into a black hole, briefly sustained a magnetic field rivaling the most extreme magnetars. That fleeting powerhouse accelerated particles to relativistic speeds, creating afterglows that lingered for weeks. It was a living lab for physics we can't replicate on Earth, proving that when neutron stars dance, magnetism leads the orchestra, and sometimes it writes the universe's most explosive love songs. J1119-6127 isn't your average neutron star. It's a cosmic identity crisis wrapped in magnetic mystery. Discovered in 2006, this object refuses to fit neatly into existing categories, blurring the line between pulsar and magnetar so thoroughly that astronomers had to coin a new term, magnetary. For years, scientists assumed neutron stars fell into two distinct camps: pulsars, with their predictable radio beats and relatively modest magnetic fields, and magnetars, the volatile giants with fields strong enough to atomize matter. But J1119-6127 shatters that binary. It spins like a pulsar, emitting steady radio pulses, yet occasionally erupts with magnetar-like bursts of X-rays and gamma rays, as if it can't decide which persona to wear. What makes this star so torn? The answer might lie in its magnetic skeleton. Most pulsars boast fields around 1 trillion Gauss, while magnetars ramp that up to 1,000 trillion. J1119-6127 sits uncomfortably in the middle at 500 trillion, too strong for a typical pulsar, yet too weak for a classic magnetar. This Goldilocks magnetism suggests it could be a transitional object caught in the act of evolving from one state to another. Some theories propose all magnetars start as pulsars, their fields intensifying over centuries as internal currents reorganize. Others speculate that violent starquakes might suddenly amplify a pulsar's field, thrusting it into magnetar territory. Then came the star's identity-shaking performance in 2016. After years of reliable pulsing, J1119-6127 suddenly unleashed a magnetar-scale outburst, its X-ray flux surging 10,000 times in a matter of hours. For months afterward, its radio pulses vanished completely, as if the star had undergone a magnetic personality transplant. When the pulses finally returned, they carried a telltale signature. The star's spin had slowed dramatically, evidence that its crust had fractured under magnetic strain, releasing pent-up energy like a coiled spring snapping. This hybrid behavior hints that the line between pulsars and magnetars might be far blurrier than we thought, with some stars flipping between modes like a cosmic switch. The implications ripple beyond classification debates. If magnetars can emerge from seemingly ordinary pulsars, it suggests these extreme magnetic fields might be more common and more dynamic than models predicted. Suddenly, every quiet radio pulsar could be a dormant magnetar, biding its time until its next explosive awakening. This reshapes how we interpret neutron star populations, stellar evolution, and even the origins of mysterious fast radio bursts. J1119-6127 isn't just an oddity, it's a key to unlocking one of neutron stars' best-kept secrets. that in the magnetic wilderness of the cosmos, categories aren't fixed. They're just waiting to be rewritten. Magnetic monopoles shouldn't exist, at least not in the universe as we know it. Every magnet we've ever encountered, from refrigerator decorations to neutron stars, comes with an inseparable pair of north and south poles. Break a bar magnet in half, and you don't get isolated poles, you get two new magnets, each with their own dual identities. Yet quantum mechanics whispers a tantalizing what if particles carrying just a single magnetic charge, north or south, might still be lurking in the cosmos like ghosts from the universe's earliest moments. These hypothetical entities, called magnetic monopoles, aren't just scientific curiosities, they're potential keys to unlocking some of physics' deepest mysteries. The hunt for monopoles begins with a cosmic paradox. In 1931, physicist Paul Dirac demonstrated that if even one magnetic monopole exists anywhere in the universe, it would explain why electric charge comes in tidy, quantized packets. His math showed that monopoles would thread electric and magnetic fields into a symmetric tapestry, resolving an asymmetry that's bugged physicists for over a century. But the real bombshell came from cosmology. Some theories suggest monopoles could have formed during the universe's infancy, when fundamental forces like electromagnetism first split apart in the searing heat of the Big Bang. These primordial relics would be incredibly massive, perhaps 10 quadrillion times heavier than a proton, making them less like particles and more like microscopic black holes woven into the fabric of space. So why haven't we found them? The answer might lie in cosmic inflation, the universe's explosive growth spurt moments after its birth. If inflation happened fast enough, it could have scattered monopoles so thinly that they're effectively lost in the vastness of space. Imagine searching for a single grain of sand hidden somewhere in the Sahara, except the Sahara is the entire observable universe. That hasn't stopped scientists from trying. Experiments like the Monopole Astrophysics and Cosmic Ray Observatory, or MACRO, have scanned Earth's atmosphere for telltale trails of ionized particles left by a passing monopole. Others, like the Large Hadron Collider, have attempted to manufacture them in high-energy collisions, hoping to catch a fleeting glimpse of these elusive entities. Even if monopoles remain hidden, their theoretical implications are staggering. Discovering one wouldn't just validate Dirac's prediction, it would force a rewrite of the standard model of particle physics. Magnetic monopoles could explain why the universe has so little antimatter, how black holes lose their charge, or even why fundamental constants like the speed of light have the precise values they do. Some theories suggest monopoles could catalyze proton decay, turning ordinary matter into pure energy, a property that, if harnessed, could revolutionize energy production or weaponry. Others propose that networks of monopoles and antimonopoles might have seeded the cosmic structures we see today, sculpting galaxies with invisible magnetic threads. The irony is delicious. After centuries of studying magnetism, we're left chasing shadows of particles that might not exist. Yet the mere possibility of their existence continues to shape the frontiers of physics. Every negative result from detectors and colliders tightens the constraints on where monopoles could hide, while new theories explore exotic hiding places, from the cores of neutron stars to extra-spatial dimensions predicted by string theory. Whether they're cosmic phantoms or lurking giants, magnetic monopoles remind us that the universe still holds cards it hasn't played, and that some of its greatest secrets might be written in the language of magnetism we've only begun to decipher. Magnetars don't just bend the rules of classical physics, they shatter the very foundations of quantum electrodynamics, revealing strange behaviors in what should be empty space. At field strengths exceeding 1 quadrillion Gauss, these cosmic monsters transform the quantum vacuum into a funhouse mirror, warping reality at scales so small they challenge our understanding of existence itself. The phenomenon at play is vacuum polarization, an effect normally so subtle it's nearly impossible to detect. In everyday circumstances, empty space isn't truly empty. It teems with virtual particle-antiparticle pairs blinking in and out of existence, a quantum foam predicted by Heisenberg's uncertainty principle. Under ordinary magnetic fields, these fleeting particles barely register, but in a magnetar's crushing magnetic grip, something extraordinary happens. The field becomes so intense it stretches these virtual particles like taffy, forcing electrons and positrons to align with the magnetic lines rather than annihilate immediately. The vacuum itself behaves like a birefringent crystal, splitting light into distinct polarization states, an effect normally seen in materials, not nothingness. Quantum electrodynamics predicts that in such extreme fields, the vacuum develops a kind of memory. Photons traveling through this distorted space don't move in straight lines. They spiral along magnetic field lines, their polarization twisting in predictable ways. This isn't theoretical. Observations of magnetar outbursts show precisely this fingerprint in their X-ray emissions, with photons exhibiting polarization angles that classical physics can't explain. The European Space Agency's XMM Newton telescope caught this signature during a rare magnetar flare in 2014, providing the first direct evidence of vacuum polarization in nature. The implications ripple beyond astrophysics. In magnetar strength fields, the electromagnetic force becomes so dominant that it briefly rivals the strong nuclear force, the glue holding atomic nuclei together. Calculations suggest that at around 10 to the 18th power Gauss, the magnetic pressure could literally tear protons and neutrons apart, dissolving matter into a soup of quarks and gluons. While no known magnetar reaches this Schwinger limit, some hover terrifyingly close, their fields strong enough to make empty space crackle with energy like a downed power line. Perhaps most mind-bending is how these extreme fields might warp the very structure of particles themselves. Electrons in a magnetar's vicinity don't orbit nuclei in neat clouds. They're stretched into needle-like Landau levels, quantized states that make atoms look more like cylindrical tubes than spheres. Atoms themselves elongate along the field lines, their electron shells distorted into bizarre, cigar-shaped configurations that would make any chemistry textbook obsolete. Under these conditions, matter doesn't just behave differently, it becomes something entirely new, a form of quantum matter unlike anything we can create in laboratories. These cosmic laboratories are giving us front-row seats to physics that defies imagination. Every magnetar flare, every twisted X-ray signature is a postcard from the edge of known physics, where the vacuum itself becomes a player in the drama rather than just the stage. As we decode these extreme magnetic messages, we're not just learning about distant stars, we're glimpsing the universe's most fundamental rules rewritten in real time. The Voyager probes carry more than just golden records into interstellar space. They carry proof of humanity's magnetic footprint. As these spacecraft crossed the heliopause, leaving the sun's protective bubble, their instruments detected something unexpected. Faint but unmistakable ripples in the magnetic fabric of space, echoes of Earth's own electromagnetic chatter. These weren't natural cosmic waves. They were the distorted remnants of our radio broadcasts, TV signals, and radar pulses, stretched and twisted by their journey through the solar wind, yet still bearing the unmistakable signature of artificial origin. Decades after their launch, Voyager's plasma wave sensors continue to pick up these ghostly signals, revealing how human-made electromagnetic noise doesn't just vanish into the void. Like a boat's wake fanning across a lake, our transmissions leave magnetic disturbances that propagate far beyond Earth. Military radars, in particular, create sharp spikes in the data, ultra-low-frequency waves that bounce along magnetic field lines, sometimes traveling all the way to Jupiter's orbit before dissipating. What began as terrestrial noise has become a faint but detectable imprint on the solar system's magnetic canvas. This raises a provocative question. could an advanced civilization light years away someday reconstruct our presence not from intentional messages like Arecibo's broadcast, but from the accidental magnetic ripples of our daily technological lives? The math suggests it's plausible. Just as astronomers study pulsars by their polarized radio emissions, alien scientists might analyze the distortion patterns in interstellar magnetic fields to pinpoint artificial sources. Our planet's most telling clue wouldn't be a deliberate hello. It would be the electromagnetic static of countless smartphones, Wi-Fi routers, and microwave towers, their combined output subtly warping the local magnetic environment. The implications stretch beyond passive detection. Future interstellar probes might use controlled magnetic pulses as a navigation system, creating temporary distortions as cosmic road signs. Others speculate that sufficiently advanced civilizations could encode messages in magneto-hydrodynamic waves, essentially writing in the language of twisted field lines. If magnetic monopoles exist, they might even serve as quantum messengers, carrying information across galaxies through their unique interactions with electromagnetic fields. Yet there's irony in our magnetic leakage. While we search for extraterrestrial intelligence through radio telescopes, our own magnetic fingerprints spread outward at light speed, unintentionally announcing our presence. Long after terrestrial broadcasts fade into background noise, the perturbations they induced in nearby magnetic fields might remain, etched into the fabric of space like fossilized whispers. Voyager's mission was meant to carry human artifacts to the stars, but its greatest legacy could be revealing that we'd already been broadcasting our existence for a century, not in sound or light, but in the silent language of magnetism. We stand on the brink of a magnetic revolution, a new era where cutting-edge tools will peel back cosmic mysteries we've barely begun to fathom. The Square Kilometre Array, or SCAR, isn't just another telescope. It's a game-changing network of antennas spanning continents, set to map the universe's magnetic tapestry with unprecedented clarity. When its thousands of dishes and antennas come online in the late 2020s, they'll detect polarized radio waves with such sensitivity that astronomers could trace magnetic fields threading through galaxies billions of light years away, potentially revealing how these invisible structures guided cosmic evolution since the first stars flickered to life. Meanwhile, the Laser Interferometer Space Antenna, LISA, will open a gravitational window into magnetism's most violent arenas. This trio of spacecraft, floating 2.5 million kilometers apart, will catch ripples from colliding neutron stars and black holes, events where magnetic fields twist spacetime itself. Unlike Earth-based detectors limited to high-frequency waves, LISA million-kilometer arms will sense low-frequency mergers, capturing the slow-motion dance of supermassive black holes as their accretion disks' magnetic fields interact. Some theories suggest these collisions might even produce temporary magnetic fireworks, bursts of synchrotron radiation visible across the electromagnetic spectrum when fields reconnect in the aftermath. But perhaps most tantalizing is how these tools could unmask dark matter's magnetic secrets. Though dark matter famously refuses to interact with electromagnetic forces, some exotic theories propose it might harbor dark photons, or weakly interacting massive particles that generate their own shadowy magnetic fields. The SKA's ultra-precise polarization measurements might catch indirect hints, subtle warping of background radio waves as they pass through dark matter halos, or unexplained synchrotron emissions with no visible source. LISA, meanwhile, could detect anomalies in black hole mergers suggesting dark matter's gravitational influence alters how magnetic fields behave during these cataclysms. The coming decades may also bring laboratory breakthroughs in quantum sensors so sensitive they could detect the faint magnetic imprint of cosmic phenomena right here on Earth. Imagine devices catching fluctuations from action's hypothetical dark matter particles as they interact with strong laboratory magnetic fields, or arrays of atomic magnetometers spotting the weak but pervasive magnetic whispers from the universe's first moments. This isn't just about new instruments, it's about rewriting our cosmic playbook. Every leap in magnetic field research peels back another layer of the universe's interconnected nature, from how galaxies form to why matter exists at all. The greatest discoveries often come from the questions we haven't even thought to ask yet, the magnetic surprises lurking just beyond our current understanding, waiting for the right tool, the right observation to pull them into the light. From the atom-crushing grip of magnetars to the delicate magnetic webs weaving through galaxies, we've journeyed through 30 astonishing realities about the universe's most extreme magnetic fields. These invisible forces aren't just cosmic footnotes, they're master sculptors, shaping everything from the birth of stars to the death throes of black holes. They twist space-time around pulsars, ignite apocalyptic solar storms, and even whisper clues about the universe's first moments. Magnetic fields don't just exist in the cosmos, they command it, bending the rules of physics to their will and rewriting what we thought was possible. Consider the sheer scale of their influence. A single magnetar's eruption can disrupt Earth's atmosphere from 50,000 light-years away, while the Milky Way's magnetic highways steer cosmic rays like interstellar traffic signals. Planets without magnetic shields like Mars become barren wastelands, while Jupiter's colossal field doubles as a particle accelerator larger than our Sun. Even in the void between galaxies, magnetic threads stretch across millions of light-years, hinting at a hidden architecture to the cosmos we've only begun to map. Yet for all we've uncovered, these forces still guard countless mysteries. Why does Saturn's magnetic field align with eerie precision while Earth's flip-flops randomly? How do black holes weaponize magnetism to launch jets that pierce galaxies? And what secrets lie in the hypothetical magnetic monopoles that could rewrite physics itself? Every discovery peels back another layer, revealing how much we still don't understand about these invisible giants. That's the beauty of cosmic exploration. The more we learn, the more we realize how much remains hidden. Whether you're a seasoned space enthusiast or just dipping your toes into the cosmos, remember, the universe's greatest stories aren't written in starlight alone, but in the silent, relentless pull of magnetism. Ready to dive deeper? Hit subscribe and join us as we keep unraveling the universe's wildest mysteries, one magnetic revelation at a time. The cosmos is stranger than we ever imagined, and the next breakthrough is just a